It really is a pleasure to be in Birmingham. I admit with some shame and regret that this is my first visit to Birmingham. I never had the opportunity to meet Rudy Piles, but of course I know of him as a physicist and as someone who created this incredible group here in Birmingham. One of my predecessors at the Institute for Theoretical Physics in Santa Barbara, Jim Langer, was a student of Piles, and so I heard over and over again stories about Piles and about how wonderful Birmingham is, and I'm glad to have the opportunity finally to visit here. Piles is someone for some of the reasons that Andy described, someone I admire greatly, and I'm sorry I didn't have the chance to meet him. I could have, but didn't. And what was really remarkable about him was the ability to create this incredible group here, but also his breadth of interest in physics, which reigned. He made contributions to all areas of quantum physics, and was a major figure. His contribution to the atomic bomb was the mistaken calculation that he made with Rich, right, which they estimated how much uranium would be necessary to make a bang, and he was off. They underestimated in a big way the amount of uranium that was necessary. I forget by what factor, at least a factor of 2, if not 10. And that was very useful because if he had been more on the mark, which was difficult because people didn't know the cross sections very precisely, maybe the project would never have gotten off the ground. Maybe that would be good, but eventually bombs would have been made. So the topic of my talk today are the many frontiers of fundamental physics. And it's sort of in the spirit of Piles that I'm going to cover many of the frontiers, which in scale range from the edge of the universe to the size of strings. Now, I'm going to talk about the frontiers, namely what we don't know. But this, of course, is on the background of what we do know, and it is always amazing to contemplate how much we have learned in the last 50 years. I think Piles would have been blown away. For example, the standard model of elementary particle physics that explains nuclear forces. But the culmination of that in the standard model, in fact, is the discovery and the understanding of the basic blocks of all matter, just about, and the forces that act on them. But also, regarding the universe and cosmology, astrophysics, in the last 50 years we have mapped the entire visible universe and reconstructed almost all of its history in incredible detail. And at the level of ordinary matter and dense matter, quantum physics, we have gained exquisite understanding and control of matter in all of its phases. All is not true because we're discovering new phases all the time. And now this control and understanding extends down to the nanoscale of atoms themselves. But I like to say that the most important product of knowledge is ignorance. That's what drives science. That's what the young people here are intrigued by, namely informed ignorance. New questions that arise based on our understanding of nature that are scientific, that can be answered by observation, by an experiment and theory. We are pushing out our knowledge into a vast sea of ignorance of which we know little except the boundaries of our knowledge. And those define the frontiers of physics. And it is those some of those frontiers I wish to discuss. And as I said, they're going to range from the largest possible scale, the universe as a whole, the arena of astronomy, astrophysics, and cosmology, to smaller objects the size of our planet or bigger, black holes, which are of such great interest due to recent observations and our great theoretical laboratories for understanding quantum gravity and nature of space and time. And then we'll go down to quantum matter. We'll go down by 13 orders of magnitude to the structure of ordinary materials. That's matter physics, where we are gaining enormous control over new forms of matter and hope to apply them to quantum computing. And finally, I'll discuss a bit about string theory and our current attempts to understand quantum gravity, the quantum fluctuations, and the structure of space and time. That's a lot, and I'll be very brief and schematic as we explore the various frontiers. Let's start with the biggest of all, subject of physical inquiry, the universe itself. And here, the big question that confronts us today, based on our enormous understanding of the history of the universe, is how did it all begin? We have developed a very good model or theory or hypothesis about how the universe began, or at least evolved shortly after whatever happened at the beginning. A theory of inflation, rapid expansion of the universe, and we have as great experimental evidence of that agrees with that model, a picture, a baby picture of the universe. Oops. Baby picture of the universe shortly after its birth. The original picture, which was a bland, homogeneous ball of radiation and matter, a hot and featureless ball, upon closer examination, looks like this. This is the Planck picture of the universe 300,000 years after the beginning, and the slight inhomogeneities here, which are at the level of 1 part in 10 to 100,000, are what, under the force of gravity, collapse and form the beginnings of structure throughout the universe, the strands of matter that are pulled together by gravity, or get denser and denser, eventually forming stars and galaxies. And the subsequent history is understood on the basis of this Big Bang theory extremely well, so much so that astrophysicists are really able to start with that initial picture of the universe and recreate it on a piece in their using our equations and our knowledge of physics in some pretty good agreement with what is observed directly. We can understand the distribution and composition of the galaxies and planets and stars and now planets, and we can extrapolate our knowledge to the future with the discovery of the acceleration of the expansion of the universe. We can start asking not just how the universe began, but how it will end. But at both the beginning and, by the way, at the end, our equations break down. And the issue of how the universe began has now become a truly scientific question, as opposed to a religious or philosophical question as it has been in the past, and one that is quite critical to completing our description of the history of the universe and providing the initial conditions for this very successful model of the dynamics and evolution of the universe. But in doing this, we need data. And the last direct information we have from light that came to us 15.7 billion years ago only takes us back to that fireball 300,000 years after the beginning. And so we continue to try to think of new ways to probe the earliest history of the universe. And they might indeed be provided by gravitational waves, which have now been detected and are very penetrating. Gravitational waves pass through the whole universe without much scattering. And so if we construct instruments precise enough, perhaps we can measure gravitational waves that originated very near to the beginning. But if that's the case, we might be able indeed to answer this question, which is a point of view of physics. The history of science is a new question. No one was ever able in the past to approach the beginning of the universe in a scientific fashion, philosophical, religious, but not by observation or by theory. Can we do that? Is physics able to explain the initial condition, the universe as a whole? Who knows? We've never been able to even ask the question precisely in the past. We don't have any idea what the answer would look like. And this is one of these questions that raises a lot of conceptual problems, to say the least. Was there a time that before the beginning of time, perhaps the universe didn't begin, it wasn't a beginning, rather it expands, collapses, is cyclic. Perhaps our very notions of time break down when we try to answer such a question. Now, the content of the universe is also a bit of a problem, since, as you know, astronomers have determined that most of the energy and most of the mass of the particles in the universe is in a form that is not the stuff that we are made out of, quarks, electrons, and light, and radiation. A good part of the matter is what is called dark matter. That means we haven't yet identified it or studied its properties. And much of the energy pressure of the vacuum, of the empty space, is what's called dark energy, because we're not completely sure what it is. And that's a bit disturbing. Most our incredibly comprehensive theory of what we observe on Earth is all based on the 4% of matter that we're made out of. The existence of dark matter is perhaps the most immediate challenge to the standard model of electric particle physics, and is the most important mystery that astrophysics and cosmology needs to solve. Dark energy as well, but dark matter is a little more immediate and measurable. So, as you know, astronomers have concluded that the rotation of the stars in a typical galaxy, including ours, around the center cannot be accounted for just by the visible matter present in the galaxy. There has to be extra dark, namely unseen, invisible matter that pulls the planets around, pulls the stars around the center of our galaxy and other galaxies, and accounts for the motion dynamics of galaxies and clusters of galaxies. There is by now no question that that must be the case, not just from motions of stars in galaxies, but motions of galaxies. And with tools, direct tools of observation of the gravitational lenses, the dark matter, like other forms of matter, bends light, and the bending of the light can be measured. Here one sees the evidence through the bending of light that comes from behind a 60 million light year long strand of dark matter, here imaged in 3 dimensions. But what is this dark matter is a question that we have been exploring scientifically now, many different ways, for over 20 years, and it's still unanswered. Dark matter could be seen more directly than these indirect tests using gravitational motion of stars or clusters or galaxies by having it annihilate in deep space. If there's dark matter, according to our understanding of fundamental physics, there must be dark antimatter. Together they can annihilate, produce signals in space. We haven't yet seen any. All matter can be created in the laboratory with enough energy, E equals mc squared. And we've been looking for dark matter at the LHC and other accelerators for many years. We haven't seen it. According to the calculations of how much dark matter there is in the universe, there are something like 500 dark matter particles passing through you every second. If one of them hits one of your the atoms in one of your cells, it can cause cancer. So it's lucky that these dark matter particles interact very weakly with ordinary matter. That's why they're dark. But that also means that we can't use our bodies as detectors and detect dark matter directly. Instead, we build detectors way underground with very little background and try to discover the rare events where a dark matter particle hits a nucleus, recoils. The nucleus recoils, or electron recoils, and we detect that. So far, again, there's no definitive detection of the dark matter wind passing through our laboratory. This is really a bit of a crisis, I think, because dark matter is unquestionably there and needs to be detected and studied. The usual assumption is that dark matter consists of very heavy particles, which might weigh a few hundred times the mass of the proton, and their interactions with light, radiation, and with ordinary quarks and electrons is very weak. That's quite consistent with simple extrapolations of our standard theory, But then we are getting to the point where it's beginning to cause a problem for the fact that we haven't detected it yet in the instruments we've built. So it could be that dark matter is some other form of matter, and there are many ideas and suggestions, and that suggests that we look for it in different ways. In any case, this is an enormous challenge for many fields of physics, astrophysics, cosmology, not to speak of elementary particle physics. Dark energy is another kind of problem. It fills the universe. It's as if the universe is filled with a fluid or substance, a very strange substance that carries energy and negative pressure. That's a very unusual kind of material, found nowhere, but the only kind of material or gas or something, substance that looks the same to all observers. Consistent with Einstein's dictum that physics looks the same to all observers. And Einstein already realized that such a form of energy and pressure would be possible in his theory based on symmetry, on the symmetry principle, the equivalence principle, and in fact stuck it into his equations in order to create a static universe. That was a mistake. The universe isn't static, and when he realized that, the universe was expanding, he discarded this term, but it's now observed and responsible for the accelerated expansion of the universe if we use Einstein's theory of gravity. It could very well, and most likely is, Einstein's cosmological constant. According to Einstein's principle, if there is such energy in the universe, throughout the universe, everywhere, same amount, it must be accompanied by negative pressure. It's the negative pressure that acts like anti-gravity and causes the universe to expand. It's very strange, but we can measure both the energy and the pressure of this vacuum stuff. And they turn out to be equal and opposite in sign to within 10%. So I regard the discovery of the expansion of the universe as a magnificent, once again, validation of Einstein's theory to within 10%. That might fail at the 1% level, and experiments will be carried out to test that even further. And if it is just, however, Einstein's cosmological constant, this strange form of energy and negative pressure in the vacuum, the universe will expand forever. And the end of the universe will be as strange and mysterious in many ways as the beginning. So here too, we are beginning to ask questions that will inform us about the end of the universe, given that the laws of physics are unchanged under reversal of the hour of time. It's always seemed to me that that's as interesting and important a question as how did the universe begin. Okay, so now I was discussing the universe at the largest possible scales. Let's come down to smaller objects which are of great interest in recent years. Black holes, which as you know now have been, we believe, directly observed when they emerge, creating gravitational waves, but also have always been great subjects for experiments that people like me, theorists with pencil and paper, carry out, theoretical experiments, trying to understand what is going on inside a black hole. So black holes, which are simply regions of space where there's so much mass or energy that light cannot escape, is pulled back by gravity. That's why these regions are black. Nothing to get out of them, at least at the classical level, were believed for many years to be crazy solutions of Einstein's equations. Einstein certainly believed that, and too bizarre to be real. Until, of course, evidence accumulated that they are very real and abundant throughout the whole universe. So it is now believed and observed everywhere it can be tested, that at the center of every galaxy there is a black hole. This is our galaxy, where we can actually measure the motion of stars around the center of the galaxy, where we can't see anything. Good evidence for a very massive object that is invisible, a mass about 1 million times the mass of the sun, which we can measure just using Newton's laws of motion, observing these circulating stars. But black holes are, much bigger black holes are present in many other galaxies that power unbelievable engines of energy that create jets with enormous bursts of radiation in the gamma ray edge of the spectrum, very energetic radiation that we detect. And most spectacularly in the last few years, we're beginning to observe the gravitational waves created when these black holes merge to form bigger black holes. And of course, you've all heard of LIGO, this exquisite spectrometer. Two of them, one in Louisiana and the other in the state of Washington, were saw the evidence for the first observed collision of black holes coming together, colliding, forming a bigger black hole, and so much energy was radiated, was emitted by conversion of the energy in the black holes to radiation, gravitational radiation, waves in the metric of space-time, that during the 1 second or so that these things were merging was more power than emitted than the whole universe. That wave spread throughout the universe, and 1-point-something billion years later arrived at Earth and caused the legs of the spectrometer, a LIGO experiment, to stretch or contract by roughly 1 part in 1,000 of the size of a nucleus. It's stupendous that they could measure that shift in the fringes of the spectrometer. It's also spectacular that using Einstein's theory, one can calculate what the signal will look like when these black holes merge. And it's really, that's required in order to distinguish this particular signal. There's one in blue and one in red from the two different sites from the noise, which is roughly a factor a few hundred times bigger than the signal. It's an extremely remarkable success of experimental and theoretical physics, and is now providing a new window, a new form of radiation whereby one can observe the universe. For example, perhaps eventually signals from near the beginning of the universe. But also the study of more ordinary astronomical objects like neutron stars, very dense collapsed stars where which mostly consist of neutrons, nuclear strange forms of nuclear matter, and perhaps in their core, quark matter, which would be very interesting. And in these collisions, again, they're so violent that they produce gravitational waves, and they were observed a year and a half ago, or almost 2 years ago. And what is really nice about these mergers was that when these are not black holes, these are neutron stars, which are visible, and when these collide, they are visible. These events, mergers, produce not just gravitational waves, but also electromagnetic radiation in all the spectrum of electromagnetic radiation, and were observed after LIGO told the various telescopes around the world, hey, look there, roughly there, because they couldn't pinpoint the event very precisely, and these violent events were observed in the X-ray, the ultraviolet, optical, infrared, and radio waves. Quite amazing. Okay, now let's go down to the atomic scale. So another many orders of magnitude. What's really amazing about our understanding of atoms and molecules, or let's say atoms, together in our understanding of ordinary matter and of new forms of matter, is that we now are working at the scale, the nanoscale, or even shorter, the scale of atoms themselves, both theoretically and experimentally. We are now learning how to understand with great qualitative and quantitative understanding matter at the atomic scale, and to manipulate and control it. And this is truly exciting, and will be, in my opinion, for the rest of this century, creating new forms of matter. Some of them we've already created, they're very surprising. Graphene is one famous example, but there are many other forms of matter which are, and new phases of matter that are being explored and understood and discovered and eventually applied. One of the most exciting applications that is driving a lot of this, and certainly the funding of a lot of this, is the desire to beat Moore's law, keep Moore's law going, and continue to expand our ability to do calculations, which is running in to severe limitations of classical computers, which are now having to operate, generate heat at the atomic level. The hope is to construct quantum computers, which do not work with ordinary qubits, ordinary zeros and ones, classical qubits, but rather with quantum qubits, quantum bits of information, qubits. We use the quantum structure of matter to construct more powerful computers. So this search began in earnest. So one of the first places it began was at the ITP, in a program that brought quantum physicists, atomic physicists, computer scientists together to figure out what a quantum computer can do. And it was early on discovered that quantum computers could be very powerful in solving certain problems that fortunately the spy agencies were interested in, like cracking codes, and which gave funding for an incredible amount of very fascinating condensed matter physics, quantum physics, and now the beginning stages of even private companies like Microsoft and Google to start building something which hasn't yet been designed. They're trying to do it. So the basic idea is that classical computers work with zeros and ones, a switch that's on or off, a circuit that's closed or open. You could think of them as spin up and spin down. But in quantum mechanics, if you think about spin up and spin down, you can also have states that are coherent superpositions that spin up and spin down. So a quantum qubit, a spin, for example, which if you measure it in one direction is either up and down, extends the state itself is really an array in a Hilbert space with much more information than just up or down. And an array of such quantum bits, one explores a space of states which is much bigger than that provided by classical bits. And two, as it turns out, can carry out certain calculations much faster than classical computers ever could, especially calculations about quantum systems. And so the goal of developing quantum computers is of great interest to many people, Microsoft and IBM and Google, because they want to make money, they want to have the next revolution in electronics, to spy agencies, of course you could use these computers to crack codes, but also the physicists, because we could use them to understand quantum systems, to understand quantitatively in detail that is beyond our capability at the moment, the structure of strongly correlated electron systems or of chemical reaction, which would be of great, great interest. The problem is that, as you're well aware of, coherent quantum states are very fragile, which is why the classical world is so robust and is what we feel. Quantum effects are easily washed out. And once these quantum bits come in contact with the environment, they rapidly lose their coherence and are no better than classical bits. So it's an enormous challenge to construct a quantum computer, theoretical challenge to understand the materials, invent new materials that can deal with this problem, and then, in addition to understanding the hardware, to start developing software to do calculations. It's an enormous experimental and engineering problem to build such devices. I have no doubt they will be built. 20 years ago, people said it would take 50 years. I think 20 years later, 30 years is probably reasonable, quite reasonable. The big companies, Microsoft and Google, intend to do it in 5 years, but they probably won't succeed. Okay, let's go down even further to the nuclear and subnuclear scale. This, of course, is the field in which I've worked most of my life, in studying the properties of the basic constituents of matter. And here, too, we have enormous success. At the end of the 20th century, we completed the construction of an incredibly successful theory of quarks, up and down quarks, and electrons and their neutrinos that, and two other families of quarks and neutrinos, and an exquisite understanding of the forces that act on these particles. Electromagnetism, responsible for, of course, the atomic structure of matter and molecular structure, and the weak and strong nuclear forces that act within the nucleus hold the quarks together permanently into protons and neutrons and other particles. And the weak nuclear force that's responsible for, that transforms one kind of quark into another, up into down, responsible for radioactivity and transmutation of elements, and so on. This theory, this is called a model, but it's really the most successful, comprehensive, fundamental theory that physics has ever had. So I could put it all on one shirt, t-shirt. There it is, just like Maxwell's equation, but much, much richer, because it has a few parameters. Only one or two are relevant for all the physics that's present in this room. The other 16 or so parameters are only needed if you want to explore what goes on in high energy collisions at the LHC. This theory is unbelievably successful. Elements of it have been tested to 1 part in a trillion, just in quantum electrodynamics. But the weak and strong interactions, nuclear forces now have undergone literally hundreds and hundreds of precision tests to better than 1%, sometimes 1 part in 100,000. Much to the dismay of many of my experimental colleagues, so far there are no contradictions and no predictions of this theory when they're made that have been nullified or shown to be wrong. There are phenomena that we observe in the universe, mostly outside the Earth, that are not contained in the Standard Model. One of them being the fact that neutrinos have a mass and mix, and that can easily be accommodated in a variety of simple extensions of the Standard Model, but we're not yet sure which is correct. Experiments are underway to tell us that. But the most important thing that is not in the Standard Model is dark matter, and which astronomers indirectly observed. So it's out there, and its nature will be greatly informative as to truly new physics beyond the Standard Model. It should really be called the Standard Theory. I've been lobbying for that for some time. This is as comprehensive a theory as physics ever dreamed of. There is literally no experiment on Earth which we, as reductionist extremists, could not argue could in principle, with the aid of a quantum computer perhaps, be calculated from this t-shirt. Aside from dark matter and neutrino masses, most of the mysteries that remain at the frontier of fundamental particle physics, fundamental physics of this type, are theoretical questions. So if we take this theory and extrapolate it to even shorter distances to see where it might fail, well, nothing much happens until you get to extraordinarily short distances, which requires extraordinarily high energies to explore. At these very high energies, the forces seem to unify. And the very nature of the laws of force that we have discovered and understood, based on symmetry principles, and the nature of the particles that we have observed and whose properties we have measured, again, suggests that they have a common origin. So, since the completion of this model, we have been searching for a unified theory of all of these non-gravitational forces. And the remarkable coincidence is that the place, the energy at which these forces seem to come together, the scale of energy, the distance, is the same place where gravity, the fourth force of nature, becomes important. Gravity is a very weak force at ordinary scales, like in this room. It's the only force that you feel. But that's because the other forces are so strong that things neutralize. So if you have, if you are charged, like you rub your feet on the carpet and you have an electric charge, and that charge you will definitely feel the electromagnetic force, but you'll immediately be neutralized by picking up an opposite charge from the environment. There's no anti-gravity. You can't screen gravity. So when I hold this up, the whole Earth is pulling down. Every atom in the Earth is pulling on this thing. And with a little bit of electromagnetic origin force, I'm holding it up. Gravity is really weak. You need a whole planet to feel it. But gravity, the charge of gravity, the source of gravity is mass, energy. So if you have objects with very big mass, like black holes, or very high energy, they'll attract each other with a force that increases like the mass squared, the energy squared. So at these very high energies, gravity becomes a very important and quantum force. And that has led us to try not just to unify all the other forces of nature, but to unify them together with gravity, which is not really understood yet as a quantum force. And that's led us to string theory. And one of the string theory has done a lot for us. I'll say a bit more about it. But the speculation that, in fact, all these particles we see, all the forces we see, are just different vibrations of a string, an extended object, is far from being answered, or even we have no direct clues that that is correct. And unfortunately, we know enough about string theory to be able to test it by post-Fichte measured things, elements of the standard model that we can't yet calculate, or explain new phenomena which we haven't seen. So it's a tricky situation. One thing is clear that string theory helps us explain is quantum gravity. And it really is the only successful attempt to understand what goes on in gravity. Gravity, according to Einstein, is the dynamics of space and time. Space and time geometry is a theory, is an object in physics with a metric. There is a well-defined notion of distance between points. And that distance is a dynamical object in Einstein's theory. When it fluctuates and changes, as like when a gravitational wave passes through, the structure of space-time is changing and fluctuating. And in quantum mechanics, everything is always fluctuating. In gravity, those fluctuations become bigger and bigger when you go to shorter distances or higher energies. And at that distance scale, where the other forces of nature seem to come together, the fluctuations of space-time itself become extreme, large. You can't treat them as you can't treat these quantum effects as small. And it has been clear that in some sense we're going to have to go beyond Einstein's theory, as he always believed, at this scale. Exactly the same scale, we believe, where the other forces of nature are comparable in magnitude. So we have been forced, just by thinking of trying to unify the other forces of nature for which we have such a spectacularly successful theory, to contemplate the nature of space and time. And I'm going to end my discussion of the frontiers with some remarks about space and time. One thing string theory brought up rather early in the game was the question as to whether there are more than 3 dimensions of space. We only directly see 1, 2, 3. You only need 3 coordinates to describe the position of particles. But there might be hidden dimensions that are wrapped in very small circles, which would not be directly visible unless you had a very good microscope. And that was always a possibility. Once space and time were understood to be dynamical after Einstein, people explored this possibility, but string theory made it more urgent because the simplest models, simplest kinds of solutions of string theory required extra dimensions, 6 extra dimensions in fact, 6 extra spatial dimensions. So that would mean that at each point, like this point right here, is not really a point, but a little 6-dimensional manifold, which is all curled up, looking something like this. And the remarkable thing, which is so beautiful, is that in such descriptions of when you try to construct such solutions of string theory and see what they would look like to a 4-dimensional, like us, macroscopic, big observer who can't see these extra 3 dimensions, the aspects of a theory like the standard theory, the standard model, namely, what kind of forces come out of this kind of theory, what kind of matter comes out, and the properties of matter, the masses and mixings of all those quarks and leptons, are determined by the geometry of the hidden dimensions, are determined by the shape of this invisible manifold at each point in space. It's a beautiful answer. And it is one of the exciting things about this approach, that these kinds of questions, you know, why do we have the forces we have? Why do we have the form of matter we have? Why do the quarks and leptons have the masses they have? These are questions that are put with answers we put into the standard model, but we can't say why, and we can't calculate those parameters. But in string theory, they're determined by the geometry. However, there's zillions of such solutions, and we're not sure what picks out one from the others. In some sense, they all have cosmological problems. And so we're not yet although we understand that a theory like string theory can reproduce the standard model with all of its aspects and a consistent theory of gravity, we're just not sure what particular model or theory within this framework is going to be picked out, if any. But string theory, this approach has done more than just provide a framework for trying to understand aspects of the standard model and predict where new physics will arise. It also is useful in this theoretical laboratory of conceptual Gedanken theoretical experiments that we've been carrying out to understand things like black holes. The black holes we discussed before as real astronomical objects, but they have been subjects of theoretical experiments since their discovery, shortly after Einstein's theory, because they immediately raised a problem which was always there with black holes. If you throw stuff into the black hole, it's lost forever. It appears that classically information would be lost. You can't see what's inside the black hole, so you've lost the information. If you write a poem, no one reads it, throw it into the black hole, no one will ever be able to read it. Information is lost. Quantum mechanically, the same is true. If you throw a correlated, entangled state of matter into the black hole, you can't see what's inside the black hole, so you have to assume anything is possible. And then what happens is that a pure quantum state becomes a mixed quantum state. You lose information. Now, quantum mechanics, classical physics as well, information is not lost. You can't lose information. So this has been a problem, especially after Hawking argued that black holes will radiate and eventually disappear. So you start out with no black hole, stuff collapses, forms a black hole, radiates thermally away its energy, and you've lost information. And Hawking argued that if you want to construct a consistent theory both of general relativity, of gravity, and of quantum mechanics, you've got to give up one or the other. He, as a relativist, was perfectly willing to give up quantum mechanics. Many of us were not. In any case, string theory really answered this question to Hawking's satisfaction. Not completely, but certainly first approximation. And it's based on a understanding that has led studies in this area and beyond for the last 20 years. And that's the phenomenon in string theory of duality, of the existence of two separate, different descriptions of the same physical phenomenon. And string theory, one has both these dynamical extended objects, strings, and one has two kinds of strings. Closed strings, cut them, they have ends, open string. And it turns out you have to have both, or you can have both. You must have closed strings, because if you have open strings, you can always close them. And open strings can end on some surface called a brane. And what has been realized is that this duality, there's a duality between describing physics in terms of the open string and or the closed strings. If you look at the dynamics of the open strings, which are attached to some boundary, those in certain situations, low energies, the dynamics is that of ordinary quantum mechanical systems, like a bunch of spins interacting. And gravity, in that limit of low energy, the closed strings decouple, you have no gravity. On the other hand, the same system can be described in terms of the closed strings, which in effect contain the gravitational center in a curved space. Now this is pretty not easy to grasp, but what it really means is that there are two separate descriptions of the same physical phenomenon. The most interesting of these dualities connects quantum mechanical systems in ordinary, familiar Minkowski space-time. That's flat space and time. That's what approximately surrounds us. We live in flat space, time, four-dimensional Minkowski space. And many quantum mechanical systems that live in such a ordinary space with no gravity, just ordinary forces, like the Standard Model. And more precisely, the best understood example is a very close cousin of the Standard Model, can be equally well described by strings moving in a curved space-time with one extra spatial dimension. So a five-dimensional, four-dimensional space and one time, negatively curved, so-called hyperbolic space. This geometry is kind of illustrated by Escher's drawing there. This duality has driven the field for the last 20 years in many, many different directions, including trying to understand the paradox formulated by Hawking, who said that black holes, the formation and evaporation of black holes violates quantum mechanics. But this duality allows us to construct examples of ordinary quantum mechanical systems with no space, with less space, and no gravity, which are dual or equally well described by quantum gravity in a bigger space. And in particular, say, a black hole in this curved space-time can be equally well described by what is called a quark-gluon fireball in the Standard Model, or a close cousin to the Standard Model. Now, since the QCD, the formation of a fireball, as seen at RIC or the LHC, which forms and evaporates, certainly does not violate quantum mechanics, and no information is lost. This demonstrates that information is conserved in the formation and evaporation of black holes in anti-de Sitter space. So the kind of black hole we have in the center of the galaxy is harder to describe. It's less symmetric, and the dual theory is less understood. But there are many, many examples of such dualities appear for most of us to resolve the information paradox and keep quantum mechanics alive. But there are many other applications of this kind of duality in elementary particle physics, in condensed matter physics. In the case of QCD, the duality is between, as hinted there, between our understanding of QCD as a gauge theory of quarks and gluons, on the one hand, with no gravity, or on the other hand, by a string in a bigger space. This is not too surprising, because string theory was actually invented over 50 years ago to try to explain the strong nuclear force, to explain the fact that we now understood later that in quantum chromodynamics, the field lines of force, the whole of the color chromodynamic field that extend between quarks, say, and anti-quarks, are squeezed by the vacuum into flux tubes. That's, in effect, what asymptotic freedom is. And it explains not just the fact that these forces get weak when you pull the quarks together, but they also get strong like a string as you pull the quarks apart, and explain confinement of quarks permanently inside nuclei. This is a picture of what happens in QCD when you pull two heavy quarks apart, and you see the flux tube being created by flux lines being squeezed. That's a fat string, and it's because of this phenomenology that people discovered string theory. So it's not too surprising that there is a dual description, we believe, of QCD, of mesons in QCD, in terms of strings. Well, we don't exactly have that yet, real QCD, but we have it for this close cousin of QCD, which is supersymmetric, has extra symmetries, is more soluble. But that means we can learn a lot, or at least for this close cousin of QCD, for very hard problems that we can't yet solve in QCD. For example, what happens in this fireball? When you smash heavy ions together, you create a fireball of deconfined quarks and gluons, a very interesting, strongly interacting fluid. QCD, nobody can yet calculate directly, but using this duality, that's related to very simple properties of these strings in which can be approached by solving, say, Einstein's equations. Not just that, it turns out that some of these quantum mechanical systems that have duals could very well, and it's been speculated, give us example of quantum critical points of strongly correlated fermionic systems, which near critical points behave like continuum quantum field theories, but in regimes that no one could ever imagine calculating nowadays, since the forces are so strong. But the dual picture, in some limit, can just be treated by solving Einstein's equation. So, in the last 10 years, we've seen hardcore condensed matter, quantum condensed matter physicists relearn general relativity in order to deduce properties of quantum critical points, which might have something to do with the kind of quantum critical points that are to explain heavy metals or ITC superconductors. But perhaps the most interesting aspect of this duality is the resolution of the problem of quantum gravity, like the black holes I mentioned, but also new concepts of space and time. Because you see, in this duality, you have a duality between a system with no gravity and one with gravity. One with less space, fewer dimensions, and one with more space. In fact, in some cases, there's no space at all on one side of the duality. No space, no dynamics of space, no gravity. On the other side, space and gravity. So, we're beginning to ask in a very serious way, with very powerful tools, what is space-time made of? Many of the properties, classical, naive properties of space-time that we're used to in everyday experience and in our theories of physics, assume certain properties of space which string theory negates in many specific examples. Smooth manifold, a fixed topology. Ordinarily, you can't change the topology without tearing space and time. It's not true in string theory. Even a fixed number of dimensions. In string theory, certain states can be described as if you have strings moving in 10 dimensions. As you vary a parameter, it looks like the strings are moving, or the objects are embedded in 11 dimensions. So even the number of dimensions loses its meaning. And most string theorists believe, that in some sense space-time is better thought of as an emergent concept. You know, an emergent concept that breaks down if you try to ask questions like, what happens at 10 to the minus 33 centimeters? Or what happened at the first 10 to the minus 43 seconds of the universe? How did the universe begin? Of course, space-time is really an emergent concept, so is gravity. But, you know, what is space-time made out of? That's a really hard question. People have thought about it over many, many, many years for a variety of reasons, gotten really nowhere. But now we have tools. We have this duality in which space-time, in the sense of Einstein's theory of space and time, emerges from a quantum mechanical system with no dynamical space and time at all. But in the general case, it's really a tough problem, especially if you try to extend what we're studying now, which is mostly the emergence of space to space-time. And how can you formulate physics? You can easily formulate physics without space. You have objects that interact. But how do you formulate physics without time? So this is the kind of problems at the frontiers of physics. And I'm not going to end here. I'm going to spend the rest of the time I don't have to ask whether this kind of frontier exploring can go on forever. And there are a variety of reasons why it might not, and I would like to address 3 of them. First, maybe we'll get the answers and construct a final theory, and then we'll be finished. We've gone as far as we can go. Maybe we're just too dumb to answer some of these questions. And the most dangerous possibility is that we'll lose the will to proceed. So let's first ask about a final theory. Is there such a thing as a final theory of physics in this sense, or do we continue to go further and further as we have been doing for 400 years? So I'd like to, as before, physicists always like to reduce these problems to geometry, so let's try to construct the geometry of knowledge and frame this question in these terms. So, what is the geometry of knowledge? Well, there is a well-known model called the onion model. I call it the onion model. And that is, knowledge is an onion. You peel away layer, and then the final answer is at the core of the onion. This model explains nothing and brings tears to my eyes. And, so I showed you this picture. We live in the sea, in this bubble of knowledge in the sea of ignorance. That's how it's an onion, inverted onion, turned inside out. And in this picture, we're always moving outwards. And knowledge is what's contained inside this bubble. Much of it is in libraries, but it's now all accessible on your phone. Ignorance, what we don't know, is only known on the boundaries of this bubble. So this model explains a lot. It explains, of course, that knowledge is increasing, like the volume of this bubble. But it also explains, as you young students are beginning to realize, that the more you know, the more you're also aware that you stop knowing. So ignorance also increases. But since we're only aware of the ignorance at the frontiers of knowledge, that's where the known unknowns are. All the other stuff we don't know that we don't know. So ignorance increases only like the surface of this bubble. So that explains why we get wiser even as our ignorance grows, together with our knowledge. So good, I've given you a model, and it explains something you've learned in your life, you wondered about. The more I learn, the more I go, I don't know. But I still get wiser. So now let's apply this model to the question of whether we can construct a final theory. So to rephrase this question, is there a finite amount of ignorance? If we had a final theory, then at least the reductionist frenzy would be no ignorance. Now this is a problem we faced before in exploring the Earth. And this is a map, a medieval Eurocentric map of the world in the Middle Ages. And you see it looks like a bubble. And the red area is where we know. That's the knowledge. We have some idea of what's at the borders, and then beyond we have no idea. And people explored the Earth. There were explorer societies. And as you know, the Earth is round, surface of a sphere. And eventually, we ran out of ignorance. We explored the whole Earth. Explorer societies shut down. We have a final map of the Earth, at least with a resolution, say, of 1 meter or 2. Final, finished, over. So the question is, more generally about physical reality, is the sea of ignorance compact? A geometrical question, topological question. Is the sea of ignorance compact? I am totally agnostic. I don't know. It could be unbounded and infinite, like the flat Earth. Or it could be compact and finite, like the surface of the Earth. It is, actually. How would we know? Well, I don't think we can know. There are only 2 ways of knowing. There's only one way of knowing. It is, in fact, compact and finite. And we finish exploring. But at the moment, there's no sign of curvature. We don't see it. But that, we didn't see the horizon, or many people didn't see the horizon of the Earth for a long time either. I think we would know if we began to run out of problems, right? So that's what curvature would mean. As we learn more, ignorance would actually shrink instead of grow. And that is not the case at the moment. But it could be in the end. Would this be the end of physics? No, of course not. It might be the end of a certain kind of physics, but most of physics is truly infinite, I believe, in its capabilities or interesting structures. Doesn't really care too much about the final theory, the theory of everything at the reductionist bottom or the top. It's really in the surely infinite number of fantastically interesting complex structures that can be created from these elementary objects at the reductionist bottom. What about the second issue? Are we dumb enough? Are we smart enough to answer questions like, what is space-time made out of? How did the universe begin? Come on. Homo sapiens have been here for, 100,000 years? We were picked out by evolution to be able to answer how the universe began, and what space-time is made out of. Natural selection perfected that ability. It seems a bit presumptuous and arrogant to argue that, especially since we're well aware that our fellow species are clearly unable to even understand quantum mechanics. I mean, I've not been able quantum mechanics. We understand there are questions that dogs cannot answer. Why should we imagine that there are questions that we can't answer? Well, I don't know the answer to this either, but I'm optimistic. There are certain things in our favor. One is, what is unique about Homo sapiens is language, from which much follows. And language, whose highest form is mathematics, has truly infinite capacity. As Chomsky pointed out, a newborn baby picks up language. How? Who knows? And is immediately able to formulate sentences that have never been uttered before. There's sort of infinite structure to language and certainly to mathematics. Now, that's good to have an infinite tool, but it might not be infinite enough. There's an experimental way of testing whether we're getting to that state. Some of you might be under the impression that we're there already, but I think not. One experimental sign is that we are faced with questions that can't be answered. Well, so far there's no evidence of that. If you look at the history of science, questions come up and can't be approached by the scientific method. They are answered usually rather rapidly. There's another way of testing this ability, and that is if it were true that we were getting to a point where the questions we ask are so profound and beyond our innate capabilities, you might predict that it would take graduate students longer and longer to get to the frontiers of knowledge. There would be this barrier, right? They would start graduating at 30, 40, 50. By the time they graduated, they would have to retire. That would be the evidence that we're beginning to, our frontiers are true barriers in the sense of the dog quantum mechanics. And there's no evidence of that. So modern physics, string theory, might appear to some of you as impossibly difficult, but today's brilliant graduate students go in at the age of the middle, late 20s are already leading the field in new directions. Finally, however, the real danger, in some ways, might be that we will simply lose the will and means to go on. So big science, which is necessary in so many areas of science nowadays, but especially in particle physics, especially in astrophysics and cosmology, is getting to be more expensive, longer time scales, and it's not clear that we can continue to convince our societies, our fellow citizens to support this. Again, I don't know. I'm always amazed at the capability of my experimental friends and technicians to keep going no matter what, but this might happen. I hope not. And I end with David Hilbert's famous saying on his grave, "We must know, we will know." Thank you.